Good morning, ma'am. My name is B. Ramu. I'm from third year EC B section from Institute of Aeronautical Engineering College. Today, I'm gonna give a presentation on the topic of application of waveform weighting for a frequency invariant transmit beam pattern. Introduction to waveform weighting. The waveform weighting is a technique used to manipulate the amplitude and phase of signals. It plays a crucial role in optimizing transmit beam patterns for radar and communication systems. This presentation explores its application in achieving frequency invariant beam patterns. Understanding transmit beam patterns. For example, I'm showing here how the beam pattern in continuous line. Beam pattern of a continuous line. A transmit beam pattern defines how energy is distributed in space by a transmitter. Beam pattern can vary based on frequency, leading to challenges in system requiring consistency. Frequency invariant systems patterns maintain similar characteristics across different frequencies, which is essential for effective communication. It means that frequencies vary, maintain a similar characteristics, different frequencies. To maintain a similar characteristics, we varies the frequencies. Basics of frequency invariance. Frequency invariance refers to maintaining consistent beam characteristics over a range of frequencies. This property is vital for systems operating in multi-frequency environments such as modern radar systems. Achieving frequency invariance can enhance signal integrity and overall system performance. Electromagnetic radiation, the frequency variation is the delta E is aligning on x-axis. The first waveform is low frequency, it having long wavelength, high frequency having short wavelength. That is the major difference between low frequency and high frequency. The role of waveform weighting. The waveform weighting allows the adjustment of signal properties to shape the transmit beam pattern. By modifying the amplitude and phase of individual waveform components, a desired beam pattern can be achieved. The adaptability is key to addressing the challenges posed by frequency variations. There are different techniques from waveform weighting. Uh, One of the technique is modulation. So by seeing a picture, we already knows what is modulation. This picture is depicts amplitude modulation. The first waveform is message signal, the second waveform is carrier signal, and the message signal having low frequency and the carrier signal having very high frequency. The combination of both, we get that we are giving these two signals to the amplitude modulation circuit. We get the modulating wave that can be shown in third waveform. The common technique include amplitude modulation, phase shifting, and delay adjustment. So one of the technique is I'm shown here. Each method targets specific aspects of the waveform to influence the resulting beam pattern. The choice of techniques depends on the requirement of the application and the characteristics of the transmitter. There are advantages are there by using frequency invariant patterns. The first one, frequency invariant patterns minimize the impact of frequency dependent phenomena such as multipath propagation. They enable more reliable detection and tracking in complex environments. System utilizing these patterns can achieve greater operational flexibility and robustness. This picture depicts that how the frequency invariant patterns can be application in radar system. The waveform weighting also used in radar system. Waveform weighting and frequency invariant patterns are widely used in radar applications such as surveillance and targeting tracking. These techniques enhance the radar's ability to detect and classifying targets across varying frequencies. This also improves the radar performance in the cultural environment where consistent beam pattern is critical. We can see the picture how the waveform weighting is used in real time. Application in communication system. In communication system, frequency invariant patterns optimizing signal transmission over a diverse frequency bands. They reduce interface and enhancing to noise ratio enhance. It enhances SNR, which is a vital for the data integrity. Waveform weighting technique can also support advanced modulation scheme, improving overall system capacity. Future trends in waveform weighting. Ongoing research aims to refine waveform weighting techniques for even great precision in beam pattern control. The integration of machine learning algorithms may lead to adaptive waveform weighting strategies. Future systems will likely leverage advanced algorithms to optimizing performance in real-time environments. So I conclude that waveform weighting is essential for achieving frequency invariant transmit beam patterns in various applications. Its application enhance the performance of radar and communication system, addressing the challenges posed by the frequency variations. Continued advancement in this field promise to drive the next generation of robust and reliable communication technologies. We can see how the azimuthal angle is there in degrees. Thank you.